Let's take a look at a Carnot cycle, which essentially walks us through a pressure-volume graph and can be used to represent either a heat engine or a refrigerant cycle. Carnot engine provides a maximum efficiency in a 4-step cycle. If we start at position A, in this case, so we have high pressure and relatively small volume. First step is going to be along this line. Remember, a curved line means it's isothermal. My volume is getting bigger, so I have change in volume is positive, and the reason that happens is heat is absorbed. So I have Q is positive. If my temperature change is equal to 0, V is positive, so work is done by the gas, so work is positive as well. So if heat absorbed, it's an isothermal expansion. So the heat that is absorbed by the gas goes to allow the gas to do work, and that work is expansion. So if we take a look at a Carnot engine, we have a thermometer that allows us to see the temperature. If we start this, we're going to watch and see what the graph does. We can see what the piston does, and as the wheel turns, that will change the size of the area the gas has. So here we'll let it run through an entire cycle, and then we'll go back and look at each part of it. All right, so we're looking at the first part where we have heat going in. We have a high temperature. We're on the red curve, as we saw before, and we have, as this shows, isothermal expansion. That gets us to point B. At B to C, we're going to curve along there. We have an adiabatic expansion. So for adiabatic expansion, we have a change in volume, as we can see from the graph. That means that work is being done by the gas. We're not adding heat, that's what adiabatic means. But because work is being done and we're not replacing the energy the gas loses by doing work, what we have is a temperature drop. So the gas is cooling. So the gas expands, it does work, and that causes it to lose energy. So internal energy decreases and the temperature drops. Okay, that takes us along the green portion. As it says on the area around the cylinder, no heat is flowing in or out, but our temperature is dropping because all that work the gas is doing is giving off energy and it's losing its internal energy. The next part of our graph is isothermal, meaning temperature is constant, compression. So our change in volume is negative. Volume is decreasing. So we have work done on the gas, and that work done on the gas is equal to the heat that it loses. So it's giving off heat, so its temperature is going to drop even more. So here we are. Again, it was an adiabatic expansion through part B, and now we're going to continue. So here we see the temperature doesn't change because it's isothermal. Again, all that energy, that heat energy, goes into doing work. So our temperature change, our internal energy doesn't change. The last part of our graph, taking us back up to our starting point, is the curve here. So we have adiabatic compression means that Q is 0. Compression means work is done on the gas. So if work is done on the gas, and when I'm not adding heat or losing heat, when I compress the gas, when I do work, that causes a change in my internal energy, and it increases, and that causes the temperature to go up. So if we take a look at the last bit of our cycle, here we're in the blue. We were in the isothermal compression where temperature wasn't changing. Now we're going to go into the adiabatic portion where we're not adding or removing heat. We watch the temperature go up as we compress the gas. So these are the 4 parts of a Carnot cycle. If we take a look at a PV graph and we look at the direction that we're following the path, if the path is clockwise, I have a heat engine. And remember, heat engines have a net work done by the gas. If I look at the PV path for a Carnot cycle and it's counterclockwise, what then I have is a refrigerator, and then that work is done on the gas. Okay, for a Carnot cycle, the heat efficiency, in addition to being work over Q hot, also depends only on the 2 temperatures for the heat source and the heat sink. So I can rewrite efficiency equation in terms of temperatures. And instead of Q, I can put T. So I had this equation from before, 1 minus Q cool over Q hot. It also will equal, based on this information, 1 minus T cool over T hot. But I must make sure when I do that I have temperature in Kelvin. So a couple of ways now that I can calculate the efficiency of a heat engine, a refrigerator, or a process that goes through a Carnot cycle. The last topic is entropy. Entropy is essentially a measure of the disorder of a system. In general, in nature, in the universe, things tend to increase entropy. The more particles I have present, the more possible arrangements I can have for those particles, and therefore the more entropy the system has. The more disorder I have, the more entropy I have, the less energy I have available to do work. Think about your room. It's actually an excellent example of this. It takes work to organize, put everything away in your room, keep it neat, keep it tidy, keep it structured. That would be a very low entropy situation. Your room tends to not stay that way if you're like most teenagers I know. Your room tends to get disorganized, disordered very quickly. That's increase in entropy. That's actually the second law of thermodynamics. Nature tends to go towards increased entropy. It takes work to reduce the entropy, so you lose energy available for work to do something else. Because in the grand scheme of things, energy is conserved. It's the first law of thermodynamics. So if I need to use energy to reduce entropy, that energy is not available to do work. So that takes us through chapter 11. We've learned about heat, energy, and entropy, and that should give you a good sense of how to tackle these problems.